Integral transform is an important mathematical tool in dealing with differential equations, linear, with appropriate boundary conditions or initial conditions. Proper choice of integral transform makes it possible to convert a partial differential equation into variables which may be intractable into an ordinary differential equation which is easier to solve, or integral transform makes it possible to convert an ordinary differential equation into an algebraic equation which is easier to manage. The solution thus obtained is the integral transform of the solution of the original differential equation. So, it is necessary to know the inverse transform to get back the solution of the original differential equation. Thus, we need to know the integral transform along with its inverse transform. Now, there are many integral transforms. Here we shall study 5 integral transforms, namely Fourier transform, Laplace transform, Mellin transform, Hankel transform and Z transform. This whole subject of integral transform will be divided into 5 chapters, chapter 6 to chapter 10. Now, here I shall start with chapter 6, and in chapter 6 we shall study Fourier transform, and this chapter will be divided into 7 modules. So, we start with chapter 6 module 1. Now, the question comes, what is an integral transform? An integral transform of a function f(x) defined in the interval a to b has the form given by I f, which we can write as capital F of y, which is equal to integral from a to b k x y f x dx, provided the integral exists and the function k x y is a known function of small x and small y, and this function capital K x y is known as the kernel of the integral transform. Now, note here that the kernel function k x y along the interval a b need not be finite, distinguishes a particular integral transform from another. In general, properties of integral transform, such as for which class of function f the integral exists, it depends on capital K, but in general all integral transform satisfy the linearity property, that is I of f plus g is equal to I of f plus I of g, and also I of c f is equal to c into I of f, where c is a constant and f and g are functions. Now, we want to know where from this Fourier transform comes. Actually, Fourier transform we can obtain it from the study of Fourier series. In Fourier series, a periodic function is expressed in terms of sine functions and cosine functions. Thus, a complicated function which is periodic can be expressed as the sum of simple functions represented by sines and cosine. This we all know. Now, Fourier transform can be thought of as an extension of Fourier series in which the period of the function is made infinity. We assume that a function f is periodic with period 2p and f(x) and f(x) are piecewise continuous functions in the closed interval minus p to plus p. Then it has the Fourier series representation in the form f(x) equal to a naught by 2 plus summation n equal to 1 to infinity a n cos n pi x by p plus b n sin n pi x by p. Here the constants a n and b n are given by a n as a n equal to 1 by p integral minus p to plus p f t cos n pi t by p dt, n varies from 0, 1, 2 etc. and b n is equal to 1 by p integral minus p to plus p f t sin n pi t by p dt, and here n varies from 1, 2, 3 etc. Now we substitute the expression for a n and b n into the expression of f(x) and we see that the representation of f(x) given in equation 1 is equivalent to f(x) equal to 1 by twice p integral minus p to plus p f t dt plus 1 by p integral minus p to plus p f t summation n equal to 1 to infinity cos n pi t minus x by p dt as given by equation 2. Now we make p tends to infinity in this representation, so that f(x) which was defined in the interval minus p to plus p, now it is defined in the interval minus infinity to plus infinity. And here we also assume that f is absolutely integrable in the interval minus infinity to plus infinity. Then we see that first term in the representation of f(x) given by equation 2 as p tends to infinity, it is equal to 0. So that f(x) becomes equal to 1 by p minus p to plus p f t summation n equal to 1 to infinity cos n pi t x by p dt. First term is 0. Now for the second term we write delta s as pi by p, so that as p tends to infinity delta s tends to 0, and equation 2 this gives f(x) equal to limit delta s tend to 0 1 by pi integral minus pi by delta s to plus pi by delta s f t into summation n equal to 1 to infinity cos n delta s t minus x delta s dt. Now we see that the summation over n equal to 1 to infinity, this summation as delta s tend to 0, this becomes equal to integral from 0 to infinity cos s t minus x ds. So that f(x) is written as 1 by pi integral minus infinity to plus infinity f t into integral 0 to infinity cos s t minus x ds dt as delta s tends to 0. Now, here we interchange the order of integration to find f(x) equal to 1 by pi integral 0 to infinity integral minus infinity to plus infinity f t cos s t minus x dt ds. This representation of f(x) given by 3 has been obtained from the Fourier series. So, we summarize this result in the form of following theorem, which is known as the Fourier integral theorem. It states that if a function f(x) is defined in the interval minus infinity to plus infinity and is absolutely integrable in minus infinity to plus infinity, then f(x) has the representation given by f(x) equal to 1 by pi integral 0 to infinity integral minus infinity to plus infinity f t cos s t minus x dt ds. This is known as Fourier integral theorem and is a very important theorem. Now, from Fourier integral theorem as given in equation 3 or rather from 3 we can derive the exponential form of Fourier integral theorem. For this we write the expansion for f(x) as given here. We write this cos s t minus x in the form e to the power I t minus x s plus e to the power minus I t minus x s by twice 2, so that f(x) is equal to 1 by 2 pi s integral from 0 to infinity and t integral from minus infinity to plus infinity f t into e to the power I t minus x s plus e to the power minus I t minus x s. Now, the outer integral over s, this can be simplified and we can write f(x) as 1 by twice pi minus infinity to plus infinity, also integral from minus infinity to plus infinity f t e to the power I t minus x s dt ts, which can be written in the form as given by equation 4, where f(x) is written as 1 by twice pi, s integral is minus infinity to plus infinity e to the power minus I s x and t integral is minus infinity to plus infinity f t e to the power I t s dt. This is in fact the exponential form of Fourier integral theorem. From this we can write the Fourier transform. Here we write the inner integral as capital Fs, which is equal to 1 by root 2 pi integral from minus infinity to plus infinity f t e to the power I t s dt as given by equation 5. This is known as the Fourier transform of the function small f t, that is capital F s is the Fourier transform of the function small f t, and from equation 4 we can see that small f(x) can be obtained as f(x) equal to 1 by root 2 pi minus infinity to plus infinity capital F s e to the power minus I s x dx as given by equation 6. So, fx given by equation 6 gives the inverse Fourier transform of capital Fs. So, in 5 we get the Fourier transform of small ft as capital Fs, and in 6 we get back the function small fx from its inverse transform as given by equation 6. Now, the way we have derived Fourier transform is a purely formal procedure to obtain Fourier transform and the inverse Fourier transform. So, we have established Fourier integral theorem and we have adopted a formal procedure to obtain Fourier transform of a function and its inverse transform. Now, we shall give a rigorous justification of Fourier integral theorem. The Fourier integral theorem, which was given by equation 3, can be justified rigorously from the following two results. First result is lemma 1, which is known as Riemann-Lebesgue lemma, which states that let fx be a piecewise continuous and absolutely integrable in the interval minus infinity to plus infinity, then limit lambda tends to infinity integral minus infinity to plus infinity fx e to the power I lambda x dx equal to 0 as given by equation 7. This is very important lemma and its proof is straightforward if we assume that fx is continuous and its derivative is bounded in the interval minus infinity to plus infinity. For this, let x lies in the interval from minus p to plus p, then we perform the operation of integration by parts in the integral minus p to plus p fx e to the power I lambda x dx, which is equal to fx e to the power I lambda p minus e to the power minus I lambda p divided by I lambda minus 1 by I lambda integral minus in p to plus p f dash x e to the power I lambda x dx. Now, it can be seen that the first term on the right hand side tends to 0 as lambda tends to infinity, because fx and e to the power I lambda p both are bounded functions. In the second term, we see that since f dash x is bounded, so mod of integral minus p to plus p f dash x e to the power I lambda x dx, that is less than equal to integral minus p to plus p mod f dash x dx, and since f dash x is bounded, so this integral is convergent for all lambda. Hence, the second term in the expression, in this expression, this second term, this tends to 0 as lambda tends to infinity. So that we get first term, we have already shown that this is 0 and second term is also 0 as lambda tends to infinity. So, making p tends to infinity, we see that integral minus infinity to plus infinity e to the power I lambda x dx equal to 0, which is the Riemann-Lebesgue lemma. Now, we remark that the assumption f dash x is bounded in this result is not required. However, this assumption makes the proof simple. Next we come to the second result, that is lemma 2. It states that if f(x) is a piecewise smooth absolutely integrable in the interval -infinity to +infinity and x is a point of continuity of f(x), then we have the result limit lambda tends to infinity 1 by pi integral -infinity to +infinity f x plus t sine lambda t by t dt is equal to f(x) as given by equation 8. Now, we prove this result. To prove this result, we first note that for p positive, limit lambda tends to infinity 1 by pi integral minus p to plus p sine lambda t by t dt. This integral is equal to, by substituting lambda t equal to u, we get limit lambda tends to infinity 1 by pi integral minus lambda p to plus lambda p sine u by u du, which is equal to, as lambda tends to infinity, 1 by pi integral -infinity to +infinity sine u by u du, and this can be proved to be equal to 1 as given by equation 9. Now, we first show that the integral 1 by pi -infinity to +infinity sine u by u du is equal to 1. For this, we choose the function f(x) equal to 1 when x lies in the interval -1 to +1 and 0 otherwise. So, in the Fourier integral expansion as given by equation 3, which is given by f(x) equal to 1 by pi 0 to infinity integral -infinity to +infinity f t cos s t minus x dt ds, here we put x equal to 0, so that for x equal to 0 f(x) is equal to 1. So, in this expression for f(x), f(x) is equal to 1. So, we find 1 equal to 1 by pi integral 0 to infinity ds into integral -1 to +1 cos s t dt, and this is equal to, after performing the inner integral, becomes equal to 2 by pi integral 0 to infinity sine s by s ds. So, that we obtain the desired result after extending the integral in the interval -infinity to +infinity. We obtain the desired result 1 by pi integral from -infinity to +infinity sine u du by u is equal to 1. So, in equation 9, we have proved that limit lambda tend to infinity 1 by pi integral minus p to plus p sine lambda t by t dt is equal to 1. Now, we use the result 9 in equation 8. That means, this integral is equal to 1. We use this in equation 8. So, to obtain that, proving 8 is equivalent to proving equation 10. That is, it is equivalent to prove that limit lambda tends to infinity 1 by pi integral minus p to plus p f t plus x minus f x by t sine lambda t dt equal to 0. The function f t plus x minus fx by t is regarded as a function of t for particular x and is piecewise continuous function for all t not equal to 0. For t tending to 0, this is equal to f dash x, which exists since f x is piecewise smooth function. So, we see that the condition of lemma 1, that is Riemann-Lebesgue lemma, are satisfied by this function, and if we take the imaginary part of the integral given by 10, we see that using 7, if we take here the imaginary part, we see that by Riemann-Lebesgue lemma we get equation 10. So, the desired result now follows if we allow p to become infinite. So, we have proved the two lemmas. Now, we will prove the Fourier integral theorem given by equation 3 rigorously. We consider the point of continuity of f x. We consider the double integral. This is the Fourier integral theorem. By Fourier integral theorem, we have established f x has this representation. So, in the double integral on the right hand side, so we have proved the two lemmas, and now we shall prove the Fourier integral theorem rigorously. To prove this rigorously, we consider the point of continuity of f x. For this, we consider the double integral 1 by pi integral 0 to lambda integral minus infinity to plus infinity f t cos s t minus x dt ds. This is equal to, after interchanging the order of integration, 1 by pi integral minus infinity to plus infinity f t integral 0 to lambda cos s t minus x ds dt. Now, performing the integration for the inner integral, we see that this is equal to 1 by pi integral minus infinity to plus infinity f t sine lambda t minus x divided by t minus x dt, which is equivalent to 1 by pi integral minus infinity to plus infinity f t plus x sine lambda t by t dt by taking t minus x as t. Now, making lambda tend to infinity and using equation 8, we obtain equation 3 somewhat rigorously. Thus, 4 is justified in this sense. Now, if x is a point of discontinuity, then f x given by equation 3 or 4 is to be replaced by f x plus 0 plus f x minus 0 by 2. Next, we derive Fourier cosine and sine transform. If f x is an even function, that is f minus x is equal to f x, x positive, then from the representation of x given by Fourier integral theorem, we get f x equal to 1 by pi integral 0 to infinity into integral 0 to infinity f t cos s t minus x ds plus integral 0 to infinity f t cos s t plus x dx ds dt. Here the inner integral of minus infinity to plus infinity we have divided into 0 to infinity and minus infinity to 0, and in the integral minus infinity to 0 we have simplified so that we get f x in this form. This can be further simplified to give 2 by pi integral 0 to infinity cos st f t dt into cos s x ds, which is equal to root over 2 by pi integral 0 to infinity f capital F C s cos s x ds for x positive. Here we have taken the inner integral, that is t integral here, as f capital F C s, and that is equal to root over 2 by pi integral 0 to infinity f x cos s x ds s positive, and this is known as the Fourier cosine transform. And the inverse cosine transform is given by f x equal to root over 2 by pi integral from 0 to infinity capital F C s cos s x ds for x positive, as given by equation 12b, and this we get from this equation 11. Similarly, if f x is an odd function of x, that is f of minus x equal to minus of f x, x positive, then the representation of f x as given by equation 3, this gives f x equal to 1 by pi integral from 0 to infinity f t cos s t minus x minus cos s t plus x ds dt, which can be further simplified to 2 by pi integral 0 to infinity f t sin s t dt sin s x ds. Now, if we write the inner integral, that is t integral, as f s s, then we get small f x equal to root over 2 by pi integral 0 to infinity f s s sin s x ds x positive, as given by equation 13, where f s s is equal to root over 2 by pi 0 to infinity f x sin s x dx s positive is known as the Fourier sine transform, and its inverse transform is given by f x equal to root over 2 by pi integral from 0 to infinity f s s sin s x ds for x positive, as given by equation 14b. So, we have derived Fourier sine transform and its inverse, and also Fourier cosine transform and its inverse. So, in chapter 6 first module, we have established Fourier integral theorem, and we have learned how to derive Fourier transform together with its inverse from Fourier series, and also we have learned how to derive Fourier cosine transform and Fourier sine transform together with its inverse transforms.